Hello, my name is Muhammad Hamza Iftikhar, and this is the Lab 3 for Physics 2211. This lab explores the gravitational interactions and orbital motion through two connected computational models. One to determine the mass of a black hole, and another to stimulate a stable figure 8 orbit for a spaceship around a planet moon system. Overall, the part 1 focuses on calculating the mass through gravitational dynamics, and part 2 focuses on achieving orbital stability using motion prediction and net forces. These are some of the key findings: that the average mass of a black hole is the one given, and the optimal spaceship initial velocity is the one that is given. These relationships let us iteratively predict motion step by step in the computational model, updating velocity and position based on the net force. And these are the update formulas and principles. The parallel component changes the magnitude of the velocity or the speed, while the perpendicular component redirects the motion. Both are essential in describing curved orbits. Every mass exerts an attractive force on every other mass. This law forms the foundation of both models, driving the star's orbit in part 1 and the spacecraft's motion in part 2. And the universal law of gravitation is the one that is mentioned. The arrows visualize the gravitational interactions acting on each body, helping define our systems and surroundings before the modeling. As we can see, there are two entities in the part 1, the star and the black hole, and three entities in the part 2, spaceship, planet, and the moon. We use the given seed, which is the Georgia Tech email of each student, mine being miftikhar7@cartech.edu, to generate a unique orbital path, compute the net force via momentum change, and back solve for the mass that produces that particular motion. This is the computational model part 1 code. By iterating through the data points, we visualize the orbit and compute several estimates of black hole mass, which converge towards a stable mean. These are the results of the part 1. This confirms that our simulation matches the expected orbital behavior, consistent gravitational force, and conservation of the angular momentum. This connects Newton's law to real orbital dynamics, that the balance of changing speed and direction keeps the orbit stable. Some of the possible sources of error include the rounding of the gravitation, the step size, which is the delta t, and the numerical precision. We start with the moon's orbital parameters, then vary the ship's initial velocity until we achieve a repeating figure 8 trajectory for part 2. The initial conditions are the ones that are in the code, and the masses and the gravitational constant are fixed, and each of the entity in the model is represented as a sphere, and the moon is initialized to the orbital velocity around the planet. This is the code for part 2. The simulation evolves step by step, predicting motion using Newton's second law for each object in the system. These are the results of the part 2, and with the initial velocity 17,500, 24,890, and 0 as a vector, the ship follows a stable figure 8 orbit between the planet and the moon. To answer the what does it mean, this distinction explains why the orbit curves smoothly instead of spiraling. Perpendicular forces redirect the motion, while the parallel forces accelerate or decelerate it. The net force is equivalent to the rate of change of momentum over time. And as I said, the perpendicular component governs the changes in direction, while the parallel component governs the changes in speed. To answer the what if the system included a black hole, star, planet, and moon, the gravitational pull from the black hole would dominate. In that complete 4-body model, its influence would be the strongest, requiring much smaller time steps and more precise calculations to predict accurately. In summary, this lab demonstrated how computational physics connects Newtonian mechanics to real orbital motion.